Okay, so I think I'm on page 6 of my current notes. And I'm ready for example 3. Would you agree with me? Yeah. So we're on page 6 of our current notes. We're ready for example 3. And it's just like the last one we did the other day. They've given me a picture, and I have to match the equation. So you may remember, well, I don't know, there's only more than one strategy, but you remember what I suggested last time? Pick a point, and again, the point I see that I know for sure is on the graph is, what is that? 6, 3 pi over 2. So if I put, I kind of just do trial and error, if I put 3 pi over 2 into equation A, for example, the answer should work out to be 6. Well, I don't know, does it? Cole says no. 2 plus 4 sine 3 pi over 2. What's the sine of 3 pi over 2? That's not going to work, is it? Nope. All right, what about the next one? 2 minus, oh, I think, wait a minute, will that one work? That one will work, won't it? Because isn't this -1? And won't that become 2 plus 4, which is 6? So there's your answer. That's the one that works. Now, question 4 is a little bit different. In question 4, they give you part of the picture and they give you the equation. Basically what they're doing there is asking you what part of the picture have they given you. Okay, so 0 to 2 pi would be the whole picture because it's a sine, be the whole picture. They're asking you, okay, what part of it did I give you? I want you to think about this for a second. Look at the equation. R equals, I know it says f of theta, but remember, just like in rectangular coordinates, when we say f of x equals something, isn't that the same as y equals? So when we say f of theta equals something, that's the same as r equals. So don't let that confuse you. Right? Now, wait a second. Is that negative right there? What happens when we have an r and we multiply it by a negative? What happens? It changes by pi. Well, look, the part of the picture they gave you was in quadrant 4. So after multiplying by -3, I ended up in quadrant 4. So where would I had to have started if I multiplied by -3 and ended up in quadrant 4? Quadrant 2. Quadrant 2. So what are the parameters or the limits on quadrant 2? Pi over 2 to pi. Pi over 2 to pi.
I guess I don't understand why, it's like, sometimes like in the last picture, it looks like there's not much of it in like quadrants 1 and 2.
Mm-hmm.
Why is that?
Well, because like the last one, you're taking 2 plus 4 times the sine. Remember that a sine value can never be bigger than 1 or less than -1. So all those values are becoming smaller, and that's dropping them all down. So you're plotting points at all those angles, but the r values have changed. So when you're at pi over 6, your r value might be like point something instead of, a bigger number. So no, it's going all the way around. and we're gonna do it on our calculator a little bit, and you'll see it going all the way around. All right, so number 4, is everybody kind of okay with that logic? That we're in quadrant 2 originally in order to end up in quadrant 4 when you multiply by a negative. Okay. All right, how about the next one? What's going on there? That's kind of the same thing, only everything's positive. Here's the original equation. I'm going to look at it rectangularly. I'm going to graph this equation instead. All right. Ooh, this is good review. Anybody remember what's going on here? What do I know about that equation? Amplitude's 3, so it's going to go up to 3 and down to negative 3. Period's 2 pi over 3. And it's a positive cosine. So would you agree it looks something like that? Would you agree with that? Now the problem tells me that's all it told me. Okay, so I need to look at the part of the graph. Okay. Let me look at the polar piece that I got. This is what I've got polarly. I have to find the part of this graph that corresponds to that. Well, first of all, these are positive. This is the point 3, 0. Would you agree with that? Theta 0, R is 3. That's right here. What's that point? Well, that's where the cosine is 0. So what theta value makes a cosine of 0? Pi over 2? But it's 3 theta, so that would be pi over 6. So this part of the graph is this part of the graph, because we're going from where theta is 0 to where theta is pi over 6. All right? Theta is 0 right here. Theta is pi over 6 right here. How do I know that? Because R is 0. Right here, R is 0. 3 cosine something, forget what it is, just something, has to be 0. What does that something have to be? If the cosine is going to be 0, then doesn't that have to be pi over 2? So this guy's pi over 2, which means 3 theta is pi over 2, so theta is pi over 6. So if you put in 0 for theta, you get 3. If you put in pi over 6 for theta, you get 0. That's this part of the graph right here. So what is your parameter?
0
to pi over 6. Now, that's in quadrant 1. So you might have been thinking, okay, 0 to pi over 2. That's what I would think. But remember, it's 3 theta, not theta. So if your angle is between 0 and pi over 2, then when you divide by 3, do you see how it ends up pi over 6? If that had been a 4 theta, it would end up pi over 8 in quadrant 1. All right, one more. What's going on in this one? Okay, so we got, basically we got the same equation. Yeah, same equation. This time we have more of it graphed. Actually, the whole thing's graphed. But we're only supposed to be looking at the part from pi over 3 to 2 pi over 3. So we've got the whole thing graphed. I'm not gonna do this, but okay, so the whole thing's graphed for us. It's the same equation. We gotta figure out what is the part that goes from pi over 3 to 2 pi over 3 look like? Alex?
I'm confused, because, the multiplier on the F side is 3, but then it reaches all the way to 6 in the graph. Like, point B is at 6.
That is wrong. That shouldn't be going to 6. That should be going to 3. Yep. Was it that way in this one too? No. So I have a feeling when he made the notes, yeah, I don't know. It should be the same grid as the last problem. Yeah, that just make that a 3. Change it in the picture. The picture's not right. You're exactly right. Does everybody understand Alex's point? Yeah, so cosine can't be bigger than 1, r can't be bigger than 3. So, make that a 3 in the picture. Okay. Pi over 3 to 2 pi over 3. There are two pieces. One of those pieces is the portion in quadrant 3 from C to D. Okay, so one piece that we're looking at is this piece right here. Now we gotta figure out what is the other piece we're looking at if we're looking from just pi over 3 to 2 pi over 3. Well, guys, I already have this drawn, so let's use this. Here's pi over 3, here's 2 pi over 3. Can we translate that rectangular piece of the graph to the polar piece of the graph? Well, I don't know. From here to here, he told us this is one of the pieces we're looking at. From here to here, what is happening to my R values? What are my R values doing as I move from C to D? My R values are getting smaller, right? So in this, right here, in this piece of the graph, my R value, and then I'll look at the blue part, moving left to right, my R values are getting smaller. Isn't that happening right here? Isn't that where my R values are getting smaller? I'm getting closer to 0. R is 0 right here. I'm getting closer to 0. So I need to find the adjoining piece of the graph where the R values are getting bigger. Well, pi over 2 to 2 pi over 3. My thought is right here, because this is 2 pi over 3. So let's look at that piece of the graph and see if that makes sense in terms of the problem. What do I get if I put in 2 pi over 3? I'm checking that point right there. If I put in 2 pi over 3, what does this equal? Huh? No. Guys, what's 3 times 2 pi over 3?
It's just 3.
2 pi. What's the cosine of 2 pi? So this is 3. So basically what you just told me is the point 2 pi over 3, that point, r theta, has to be on the graph. Is that the point right up there? It is. So we're looking at the interval from D to whatever point that is, D to A. Because I have to be positive, increasing, positive, increasing, right there. You guys have only graphed one of these on your calculator. It wasn't a shape like this. But when they graph, and I don't have a very good graph here, but when they graph, it's consecutive, guys. It's consecutive, so it looks like that. So it starts here, comes around,
That's
comes
the Scottish.
around. and
That's the
comes
Scottish
around.
symbol for like Trinity.
I don't know.
Scotland, eh?
It's called.
Talking about a 3-leaf clover?
No, like there's like a. Hold on.
Cole's about to teach me some shit.
Yeah,
My
if
dad's
you can
Scottish,
tell,
cause
that,
like
that the problem is, the piece that they gave you, this piece, that's not
So I
pi
don't know,
over
but
3
like,
or 2
what's
pi
the,
over 3.
like,
Never mind.
what is,
Father, Son, Holy Spirit.
how's that Scottish stuff? Like, what's the relationship?
Well,
It's like a Norse symbol.
I don't know.
Oh,
I'm not
yeah,
gonna
yeah,
say
it might
one
be
way or
Norse,
the other.
yeah.
I'm
Look it
gonna
up.
say you should
Probably
understand enough about
Gaelic or
how the
something?
graph works and its symmetry
Well, that's Irish.
to know that's the
Well, it's-
answer. But if, I don't know.
Scottish Highlands, too.
Declan?
Oh yeah, on the same line.
Just figure that out just based on the, like, domain restriction that I gave you.
Well, that's what his question was, but here's what I need you to understand. What's this point down here? That's 4 pi over 3. Okay, you see the danger in what you're saying? Because 4 pi over 3 isn't in that domain restriction. That point ended up down there because it started out up here. So, if you can understand all those moving pieces, yes. But that is not in the domain. That angle, 4 pi over 3, is not in the part of the domain that we were given. Right? And yet that piece of the graph is in that part because of the negative value.
So I understand the logic of what we did, but like, what exactly were we looking at?
Our job was to figure out which piece of the graph corresponded with that little fixed interval that he gave us.
Okay.
Because 0 to 2 pi would generate the whole graph. So his question is, what would that little chunk?
So we were just trying to like match it with the.
Yes,
Okay.
and I matched it with this, but you didn't have to do that, you could have matched it with something else.
Directions say they consist of 2 pieces.
Mhm.
One piece is from C to D.
Mhm.
That's the answer for D2. So is it both? C and D?
No, direction matters. C to D is different than D to
Oh, yeah.
C, yeah.
How do you like find, like if it's C to D, how do you know that you're going this way instead of this way?
This was C,
Yeah.
okay, so, well, first of all, and again, this is a huge advantage I have because I graphed a lot of these. We know we started at 0, because that was from the last problem where we always started at 0. And when these things rotate through, the arc, it's not, there's no bumps and jumps. It's a nice smooth arc. So it's never going to go here and then all of a sudden have a cusp or something and go this way. It's just not. It's going to always flow around like that. Just like here, Olivia, it's always going to flow like this. Okay? Pieces of this, like that's a positive piece and that's a positive piece, but you're never gonna connect them because it's all gotta be some nice little,
How could you not do like D to B? Because like
do what now?
D to B in
D
quadrant
to
1,
B, where's
in
the?
quadrant 1 is number or letter A.
Okay, so again, D to B is going counter to the way the problem needs to go. So B, okay, the problem starts at 0. That's the beginning. So it's going to have to go this way.
Doesn't it go from D to B, like on the bottom half at the end?
Okay, but that would be, the only way to get from D to B negative would be to have negative thetas. Do I have negative thetas in my problem? No, I'm going from 0 to 2 pi. So yes, just like there's lots of ways you can name ordered pairs, there's lots of ways you can follow this curve, but not if you're starting at 0 and going to 2 pi. It's going to be a positive. And we know that actually from the problem we already did. That's how it starts right there. Okay? Your polar curve, I gotta be careful with the word never, but I don't know of a situation where your polar curve is gonna start negative. Okay? You'd have to have some negatives in there somehow. All right, let's look at the next page, and let's get our calculators out. Maybe this will make a little more sense to you after you have graphed a few of them. Oh yes, we're going to be graphing in polar. So on the back of that page that we just did, on the back of page 7, we're going to graph the two equations in number 2. So make sure you're in polar mode. I can't remember how our window was set. So theta needs to be min 0 max 2 pi. And then what did we...
The left step is there.
Yeah, and then, let's see, we need to have at least, x and y need to be at least negative 6 and 6. So I'm just gonna make them negative 6 and 6. I'm gonna put in my new equation, which is 5 cosine theta. Oops. And what shape did you get? You got a circle. Now, what? Oh, you did both of them, okay. So if the thing you got does not look circular, it should. What was the little trick I told you last time? Zoom square. Now it should look like a circle. All right, now graph the second one. Negative 2 cosine theta. You can do them both together if you want, or you can get rid of the first one and do the second one. What do you notice about that? It's smaller, and that should make sense to you. Why is it smaller? Because the amplitude number is less, the 5 and the 2. If there's something else different about it, what else is different about it?
Negative.
It's on the negative side. Boys and girls, cosine is x, right? Cosine is x. Where are positive x's? On the right. Where are negative x's? On the left. So that makes sense, hopefully. Okay, now, do you graph the ones in number 4? What do the ones in number 4 look like? Maybe you have a guess. What happened with the ones in number 4? Were they also circles?
Yeah.
But now what? Their positive sign is going to be high, and a negative sign is going to be low. They're circles. Obviously, they're not the same size because one of them has an amplitude number of 4, and the other one has an amplitude number of 3. What can you tell me about the radii of those circles? What's the radius of 4 sine theta? You think the radius is 4?
No, it's 2.
2.
2, yeah.
The diameter is 4. Does that make sense? Yeah, because what is the biggest that sine theta can be? 1. So what is the biggest that 4 sine theta can be? 4. So the biggest it can be is 4. So the radius is going to be halfway. So you get halfway point. The radius is going to be like the midline of the curve. If you were graphing it rectangularly, that's going to be like your midline. Okay. All right, go to number 7 now. Number 7. Leave everything the same and just put in this equation. Actually, put in all 4 of them and just do a quick little sketch on those grids so that you can remember what's what. It's going to get too confusing. So just a quick little sketch of each one of those. These will not be circles. Just do a quick rough sketch. Okay. These are not circles, correct? Yeah. These are what we call roses. You should be getting things that look something like flowers. So your little sketches don't need to be perfect, just kind of, just so you can remember. We're going to compare and make some conclusions. What do you notice about these? Do you notice have you made any kind of generalizations here?
The first 2 have like the same amount of like thingies as like the
Petals.
petals, like as the thing next to the theta.
Okay, so Cole says that the first 2 equations, the 3 theta and the 5 theta equations, have 3 petals and 5 petals respectively. Would you agree with that? Furthermore, can you tell for the first equation, 5 cosine 3 theta, how long are those petals? They're 5. How long are the ones in the second equation, -4 cosine 5 theta? How long are those? 4. So the number out in front is guiding us as to how long our petals are, like our amplitude. And then the coefficient on theta, for the first 2 anyway, tells us how many petals or leaves we're going to have. What happened in the third problem? When there's a 2 theta, there ended up being 4 leaves. And when there was a 4 theta, there ended up being Should have been 8. They might have been all squished up in there, but there should have been 8 of them. So question 8 says, how can you tell from the equation how many petals there will be? Well, if the coefficient on theta is odd, that's how many there are. But if the coefficient on theta is even, there will be twice that number. Okay? Now, were you watching closely when your calculator was graphing? What happened? Where did it start? Like when you typed in the equation and hit graph, where did the graphing start? Did it start at the origin, or did it start somewhere else? It started right out here, right? Every time? And the reason it started out there was these were cosine equations, right? And what's the cosine of 0? 1. So it's going to start at 3 times 1, 5 times 1, whatever it is, times 1. All right. Now, let's do exactly the same thing for the equations in number 10. These are the same kinds of equations, but they are signs. I wonder what that will change. This period's almost over. This has flown by. Oh, Lordy. Okay. Well, we don't have time to do all of them, but I think you've done enough to tell. What did 5 sine 3 theta look like? Was it another rose? Did it have 3 petals? And were they 5 units long? Okay, so all that's the same. What is different about the rose? What? Okay, they are now rotated, which makes makes complete sense, because when you think of a sine and a cosine, when you graph a regular sine and cosine, your BFFs, aren't they the same curve, just shifted? So in a circular system, we've just rotated them. Now, last question, number 12. How could you determine the angle between the petals? This is easy. You can do that. How do we determine the angle between the petals? How many there are, divided by, or divided into, I should say, 360, exactly, or 2 pi. So if there's 4 petals, there'll be 2 pi divided by 4. Oh. If there's 8 petals, there'll be 2 pi divided by 8. Okay? All right, we're going to do a little bit more with our calculator. Time got away from me then. And then we'll start 3.15. So I'm going to go ahead and assign 3.14 homework, even though we're going to do a little bit more practice with it. So that will be due